All right. And then homework 2.8 is due tonight. Okay. So if you need, some of you guys are, requesting extension requests. I need a little more time, right? That's fine, right? Request those extensions. I'm happy to give them. Okay. I'd rather you do the homework late than not at all. All right. So we'll take our, and then reminder, right? No calculators. All the numbers will be very manageable, I think. Okay. Um, if you know how to multiply two integers, you should be fine. Right? All right. So I think that's all for announcements. So today we're actually starting new material that will be on exam 3. So I've handed out 2.9 titled Building a Function from Words. And this section is very calculus-like, okay? So what we're doing is setting up the equations, and we're solving a couple of problems we actually solve because they're quadratic in nature, and we can find the maximum of a quadratic function using the formulas. But in math, for those of you who are going to take Math 120, you'll actually use calculus, right, to solve these problems. Okay. So there are 4 basic steps in solving word problems of these types, and I suggest you write this at the top of your page. The first step is draw a good picture. Okay? I think I've talked in the past about visualization in mathematics, right? Visualization is very important, right? The better you can visualize things, the better off that you are, right? And so drawing a good picture is part of good visualization, okay? Second, define your variables. What does X represent? What does Y represent? So forth. Okay. And then 3, set up the equation that describes the situation that you're modeling. And then 4, solve the equation. Okay, so those are like the 4 basic steps, right, that I go through. Right? First, I draw a good picture of what we're trying to accomplish. I define what my variables represent, and I set up the equation that describes the situation, and then I solve the equation. Okay. So in example 1, we're given a rectangle has area 16 meters squared. Express the perimeter of the rectangle as a function of the length of one of its sides. So, draw a good picture and draw a rectangle. And the area of this rectangle is 16 meters squared. And so I'm going to let X represent the width of the rectangle and Y represent the length. Okay? And so these two ends, these two sides of the rectangle have length X, and the top and the bottom have length Y. Okay? So X is the width of the rectangle, and Y is the length of the rectangle. Okay? Now the area of a rectangle is width times length, right? So area is equal to width times length. Well, the area in this case is 16 meters squared. X represents the width and Y represents the length. So we have this constraint, 16 is equal to X times Y. Right? This is actually a constraint. So if I solve for Y, I'm going to divide both sides by X. And when I switch the two sides, I get the length of the rectangle is equal to 16 divided by X, the width. Okay. So now let's set up part A. Express the perimeter of the rectangle as a function of the length of one of its sides. So you know the perimeter, recall P, right? The perimeter P is just the distance around the rectangle, right? So it's starting with this side right here. The perimeter is X plus Y plus X plus Y, correct? So P is short for perimeter. So the perimeter P, combining like terms, is 2x plus 2y, right? But what's y equal to? 16 over x, right? So I substitute 16 over x for y. And now, since I'm writing the perimeter as a function of x, we might replace p with f of x, okay? To indicate we're writing the perimeter as a function of x. So y is equal to 16 over x. And 2 times 16 over x is 32 divided by x. So we've written the perimeter P as a function of x, the width of the rectangle. It's equal to 2x plus 32 over x. And in Math 120, you'll use calculus to find the optimal value of x. Okay? In B, it asks you what is the domain of this function. Okay? So, right, function of x. So can x be negative? No. Can x equal 0? No. X has to be positive, right? It has to be greater than 0. Okay. And so in interval notation, right? All positive numbers, parentheses 0, comma, infinity. Okay. Now that might seem silly, okay, that x could be 1 trillion, right? But if x is 1 trillion, right, if the width is 1 trillion meters, then y is really, really, really small, and you still got width times length is equal to 16. Okay? So there's no limit to how big x can be. Okay? And the larger x is, right, the smaller y will be. Okay? But their product will still be 16. Okay? All right. So any questions on that? Okay. In example 2, A rectangle has a perimeter of 20 meters. Express the area of the rectangle as a function of the length of one of its sides. Okay? So we're doing the same setup. Okay? You got a rectangle. X is the width, Y is the length. Okay? But now we're given the perimeter. The distance around the rectangle is 20 meters. Okay? So using that information, we're going to write the area of the rectangle as a function of x. Okay? So the perimeter P is the distance around the rectangle, and again, it's 2x plus 2y, right? Just like over there. So the perimeter P is equal to 2x plus 2y, just like in the previous example. Okay? But in this case, the perimeter P is 20 meters. And now when we solve for y, okay, let's subtract 2x from both sides, right? And so we have 20 minus 2x is equal to 2y. And then when you divide both sides by 2, remember you gotta divide both those terms by 2, right? You have 20 over 2 minus 2x over 2 is equal to 2y over 2. Now I'm going to switch the two sides of the equation, right? The 2's cancel on the right, and we're left with y. And then 20 over 2 is 10. 2's cancel in the second term, and we're left with minus x. Okay? So the length y is equal to 10 minus x. Okay? So in A, we got to write, express the area of the rectangle as a function of the length of one of its sides, right? So area is width times length. So in this case, area using variables is x times y. And what's y? 10 minus x. So we can write the area as a function of x, which is x times 10 minus x. Okay. Now over here, x could be any positive number. Okay? But that's not true in this case, is it? X has to be greater than 0, okay? But the perimeter is constrained to be 20 meters. So X can't be 1 trillion in this case, right? I mean, it's because of this constraint, or more, this constraint. So the smallest, X has to be at least 0, but it can't be over 10. Otherwise, the length Y is negative, okay? So in B, the width x has to be greater than 0 and less than 10. Okay? And so in interval notation, that's parentheses 10, or parentheses 0, comma 10, parentheses. Okay? Any questions on that? In example 3, an open box is to be made from a rectangular piece of cardboard. 10 feet by 4 feet. So let's draw a rectangular piece of cardboard, 10 feet by 4 feet. Right? So the width is 4 feet. And the length is 10 feet. Okay. And we're going to make a box with an open top, right? It doesn't, you can't close the top, right? The top is open. Okay. So an open box is made from a rectangular piece of cardboard, 10 feet by 4 feet, cutting squares of side length X feet from each corner and folding up the sides. So out of each corner, we're going to cut a square, right, that's X feet by X feet. We're going to do that in all 4 corners. Okay? And then, once we cut out the corners, we're going to fold up the sides. Okay? So the height of the box will be X feet. Okay? Because when we fold up, cut out a corner, then we fold up the side, right? It'll be X feet tall. Okay? Find an expression for the volume of the box as a function of the size X cut out at each corner. Okay? So, after we cut out the corners, and then we fold up the sides, right? This is the base of the box right here. Right? This is the base of the box. Okay? Well, the total length of the piece of cardboard is 10 feet, right? So when we cut out this square of X feet on each end, we remove 2X feet from the length, right? So this length here, the base, is 10 feet minus 2 times X. Okay? And so then you see, okay, that X plus 10 minus 2X plus X equals the total length of the original piece of cardboard, 10 feet. Okay. Now when we cut out these squares, each length, right, each side is length X, the width of the base of the cardboard box is going to be 4 feet minus 2X. Okay. So this length here is length 4 minus 2X. Okay? 4 minus 2X plus X equals 4 feet, the original width of the cardboard. Okay? And then the height of the cardboard is going to be X feet, right? The size of the square that we cut out from each corner. So now we can express the volume of the box as a function of X, the size of the corners that we cut out from each size of the corners that we cut out from the original piece of cardboard. So you know volume, V of X, okay, is equal to length times width times height. Okay? Area is length times width, or length times width, but volume is length times width times height. Okay? Well, what's length in this case? The length of the box is 10 minus 2x. What's the width of the, right? Because the length of the box is 10 minus 2x, because that's the length of the base of the box. The width of the box, right, is 4 minus 2x. And the height of the box, size of the square, right, x feet. And that's all we got to do on this, right? We have expressed the volume of the box as a function of x. Okay? Okay. Any questions? And then in Math 120, you'll use calculus to find the optimal size box. Okay. What's the optimal size square cut out from each corner to maximize the volume? Okay. I mean, that's a legitimate manufacturing question. Okay, for those companies that make cardboard boxes. Okay. All right. You want to take your quiz, or you want to do question example number 4? Which would you prefer? All right. So we'll stop right here for today, and we'll pick up example 4 first thing on Friday. Okay.